Okay, so the first one, the inner chapter C, you're right, is short. Is a couple of dozen slides. And I think the main idea behind inner chapter C is to hammer home the idea that molecular orbital theory is where it's at. I mean, we use the valence bond theory to great advantage, but when you're trying to predict outcomes, especially where energy is involved, molecular orbital is where it's at. Now, that's, in fact, you could probably get a graduate degree in molecular orbital theory. It's so complicated. And I'm the last person you need to come to give you details on large molecules, right? Small molecules I feel fairly comfortable with, but large molecules and some of the slides in here, we're just going to have to accept Dr. Carty's premises and go with it. But yeah, I don't think he will. He's fairly reputable. Okay, so in previous chapters, we've introduced the concept of using curved arrows to move electrons. And we've described the flow of electrons during a chemical reaction from electron rich to electron poor. And to do that, we've used Lewis models. But there's another theory that's an offshoot of molecular orbitals called the frontier molecular orbital theory. Frontier is like the highest energy level for any of the reactants. The electron-rich species is going to produce the highest occupied molecular orbital. So this would be the nucleophile. And the recipient is the highest occupied. Yeah, that's right. And the LUMO is the lowest unoccupied molecular orbital. And this would be the electrophile. We could also call this the Lewis base. And this the Lewis acid. So those are the central ideas in the frontier molecular orbital theory that we're going to try to apply to elementary chemical reactions. One fringe benefit is when we consider and we're talking about overlap, when this molecular orbital significantly overlaps this molecular orbital, it reduces the amount of energy required to get that reaction to go. So if there's a lot of overlap, that also speaks to the stereochemistry of the reaction. You know, what angle does it approach? Does it approach from the side, from the top, from the front or the back? And we'll get into more of that in subsequent chapters, probably in the we'll see most of that in the second term, where we can predict the stereochemistry. Okay, remember the energy diagrams where you have energies on the y-axis and the reaction, the progress of the reactions on the x-axis. And you see the energy of the reactants in the first position on the left, like here. That's the energy of the reactants. And you go through a transition state. In this particular representation is of an exothermic or exergonic, I think is the proper term, exergonic reaction, because products are at lower energy than the reactant. But for our immediate discussion, we're going to focus on kinetics. Kinetics happen right in here with activation. Well, the activation energy is here. This is the transition state. Or sometimes it's referred to as the activated complex. It takes some energy to get there. The less energy it takes to get there, the faster the reaction is going to go. That's how catalysts work. Except catalysts work by providing an alternate route for the reaction to proceed. But in this case, if we can get the activation energy to be lower, the reaction is going to occur faster. And there are two terms that we use here. One is allowed versus forbidden. I'll talk about that a little more later. So there is an energy barrier to a reaction. And the reason for that is that the transition state is less stable. We have to add energy in there to get it over that hump. Okay. So what we need is the largest overlap of the HOMO and the LUMO in order to reduce the energy barrier for the transition state. The more overlap we can get, the better it is. And if the overlap is significant, very, very large, we say that the reaction is allowed. These are two relative terms. We can't put an absolute value on them. If there's very little overlap, then we say the reaction is forbidden. This is a representation of what you might see. For one reactant on the left, its highest, it is the electron-rich species. We just have to define it because you can't just look at them and say one's rich and one's poor. We have to define them in advance, that the one on the left is the electron-rich. So its highest occupied molecular orbital is where the pair of electrons is coming from. And the lowest unoccupied molecular orbital is for the electron-poor species on the right. And we see that the energy difference between the two, between the HOMO and the LUMO, is very small. And that's good. That also implies overlap, more overlap of the orbitals. Now, when we just focus on the two, the HOMO and the LUMO on the right-hand plate, we see that we're going to generate a combined molecular orbital based upon the overlap of those two. And you remember how molecular orbitals work. Or do we need to review that? Did I hear something? No? Yes or no? Okay. If you studied it recently, then it should be fresh. But you remember that the atomic orbitals that go into the mix, you have to come out with exactly the same number of molecular orbitals. And the way you do that is you produce a mix of bonding orbitals and anti-bonding orbitals predominantly, but you can also have some non-bonding orbitals in there also. And generally speaking, the anti-bonding orbitals, actually, this is always true. Anti-bonding orbitals are higher energy than either of the combined atomic orbitals that go into the mix. And the bonding orbitals are lower energy. So as we put electrons into the molecular orbitals, they go in according to the Aufbau principle into the lowest energy levels first, and you build from there. Okay. All right. So this energy difference, this delta E between the HOMO And the transition state is an energy advantage. It allows the process to proceed. So this slide aims to simplify the process. In other words, there are elementary steps that are the reverse of each other. When we say coordination, that's the formation of a bond by the donation of an electron pair from one species to the other. And heterolysis is you break that bond and that electron pair goes one direction only. Those are like opposites, the opposite sides of the coin. Nucleophilic addition and nucleophilic elimination are opposites. They are reverse of each other. And electrophilic and addition and electrophile elimination are reverses. So if we establish that that one of the others of these, the coordination, say, the additions, whether nucleophilic or electrophilic, if they're allowed, then the reverse reaction has to be allowed also. And that's based upon the principle of micro reversibility. The reaction has to be reversible. Now, when I saw that statement, I said, okay, that sounds reasonable. But if we look at the energy diagram and you're trying to go in reverse, now from products to reactants, welcome. When you try to go from products to the reactants, look at the difference in the energy barriers. The energy barrier is greater to go in reverse. So I've always understood these reactions to be less favorable going in reverse than they are forward for the exergonic type reactions. So with that understanding, allowed versus forbidden, those are relative terms. It might be allowed to a certain extent or forbidden to a certain extent, but like I said, they're not absolutes. But they do allow us to draw certain conclusions that help relieve some of the stress of trying to work the reverse reaction as an independent mechanism. And here's that microscopic reversibility just simply means that let's see, I want to put this in, I don't want to confuse you and me at the same time. When we say a process is reversible, and we introduced the microscopic idea here because all processes that I'm aware of in the physical world, whether they're chemical or physical, are irreversible. But at the microscopic level, we have to make this theoretical assumption that, and particularly for elementary steps in a chemical reaction, the reverse process is allowed. Both, you can go forward or backward just as easily. And that's generally where we come from in the sciences, is from the theoretical, and then we introduce fixes to it, to use a scientific term. Sometimes we call it fudging. So this concept, this frontier molecular orbital theory, is focused only on the energy barriers of the elementary steps. So that's why we're focused on kinetics only. The energy barrier determines how fast the reaction goes. And I don't know if you had in general chemistry this idea between thermodynamically allowed versus kinetically allowed. They're two different concepts, and it could be kinetically allowed but thermodynamically forbidden, and then you have to decide which one wins. But right now, we're only talking about kinetics. Okay, so we're going to look at some examples here. And this is the way we would have written the proton transfer before, where the Lewis base, or the electron-rich species, the nucleophile, with its HOMO, its highest occupied molecular orbital, approaches hydrogen chloride with its LUMO, its lowest unoccupied molecular orbital, and the HOMO is always applied to the electron-rich species. The LUMO is applied to the electron-poor species, always. Whether they have a charge or not, it doesn't matter. In fact, the charge is irrelevant at this point. And we get the reaction where we produce water plus the chloride ion. And the chloride ion happens to be a good leaving group because it's very stable. If we look at this in terms of pictorially, in terms of the orbital shapes, then we can imagine this overlap of the HOMO from the hydroxyl ion with the LUMO of the hydrogen chloride. Okay, that's the simplest example we've got so far, this proton transfer. And we're saying that this reaction is allowed because of the substantial overlap, which reduces the energy barrier, the kinetic barrier of the activation energy. When we get that overlap, that reduces. Now, what would happen if the approach was from the side? If we approach from the side, we don't get the overlap that we want. So that direction of overlap is forbidden. It has to approach from the side. And this, we're starting to introduce ideas that are going to be useful for understanding stereochemistry here, because stereochemistry outcomes in a reaction depend on the approach of the nucleophile to the electrophile. And this is actually just occurred to me. This is only a significant issue for the bimolecular reactions. For the unimolecular reactions, right, they just happen. You don't have an approach where stereochemistry outcome is significant. All right, so here's another SN2 reaction. Okay, we've got a bimolecular nucleophilic substitution. That's what SN2 stands for. So this nucleophile, the hydroxyl group, approaches this methyl chloride, and it attacks the carbon, which is electron deficient. So the highest occupied molecular orbital comes from the hydroxyl. The lowest unoccupied molecular orbital is found on the carbon of the methyl chloride. And this is what the artist would, this is our supposition. This is what we would expect to see if we were small enough to see the orbitals. And we get substantial overlap between the HOMO of the hydroxyl and the LUMO of the carbon on that methyl chloride. And again, if it approaches from the wrong direction, you don't get the overlap. So that angle of approach is forbidden. It has to approach from the left. Doesn't really have much option. Aside from the fact that you don't get orbital overlap, you've got steric hindrance on the other side, because that's where the leaving group is located. So it just makes sense that it would approach from the left, as shown in that picture. What about bond formation? If the bromine or the bromide ion approaches this carbocation, we know it's going to go for the carbon, because that's the deficient in this molecule, and it's going to provide the LUMO. So that attack forms the 2 electrons from the bromine form the bond with the carbon. That's a coordination bond. And it should look something like this. Now we know that carbon, because there are only 3 groups around that carbon, we can go back to our VSEPR model, and we see that carbon is sp2 hybridized. It's trigonal planar. So the positive charge is distributed among the unfilled p orbitals. Remember, if you've got sp2, there's an extra p orbital that's not being used. And that's where the deficiency occurs, in that unused p orbital. So when the bromine approaches, it can approach from either side and make the bond. Now, in this case, the stereochemistry doesn't change, because that carbon still has 3 identical groups on it and only 1 different group. So you don't get a different stereochemistry in this approach. But if we had 2 of those methyls were different species, then the approach from one side or the other would produce a different stereochemistry for the outcome. We just keep that in mind, because we're going to see it again later, maybe much later. But in this case, the approach can't be from the top or the bottom, because of the methyl groups. They're in the way. So it has to be from one side or the other, and they're just as likely. And so if you could track the outcome from the left-hand approach versus the right-hand approach, you should get a 50-50 mix for your outcome. All right, that was coordination. Heterolysis is the reverse of this. Right, so we break the bond. As a microscopic reversibility says that this one should be allowed also. And actually, now that you think about it, how do you get an overlap of orbitals when you're breaking a bond? Right? That doesn't make any sense. So the fact that heterolysis is the reverse of coordination, that it seems to me the only approach you can have to that is, if coordination is allowed, heterolysis must be allowed. Does that make any sense? Because you don't have any overlapping bonds to deal with, right? You might produce some afterwards, but then they go their separate ways. The leaving group is gone. And I guess it could reapproach, form, it could come back and do the reverse reaction in a situation where you have equilibrium. But that's not a kinetic problem. That's a thermodynamic problem. Okay. So if we compare nucleophilic addition to elimination steps, they're the reverse of one another. If we look at the addition step, where we can speak to this in terms of the frontier molecular orbital model, then we have the hydroxyl approaching this electron poor carbon on the carbonyl chloride. And notice that right now we have 4 bonds to that carbon. Right? So if the HOMO and the LUMO do overlap and we get a bond with the hydroxyl, then we've got to break another bond. You can't have 5 bonds on a carbon. That is technically forbidden. So that's why the double bond has to break. So now we're going to introduce actions that involve the anti-bonding orbitals. Right? We haven't looked at any like that yet. So this option, when you get the approach of the hydroxyl with its HOMO, is attacking the carbon with its LUMO. The LUMO on the carbon is a pi star bond. Now, this is where we're just going to have to take his word for it, because this molecule is way too complicated for me to draw a representation of whether the pi bond is actually the highest, the lowest unoccupied molecular orbital. We just have to assume that he's correct. But the overlap here is the key point. And you get, on the left-hand side, you get the HOMO is a non-bonding orbital from the nucleophile, and it's overlapping the LUMO, which is a pi star bond on the carbonyl carbon. But there's another option here. You can also approach that carbon from the opposite direction. And now you still have the non-bonding orbital from the HOMO approaching the pi star LUMO from the carbon, but remember, these are probabilities. In other words, these orbitals are not something that we can see, but they give us a probabilistic scatter of possible electron locations. And in this case, we've got two lobes that approach from one side or the other. Now, if it approaches from one side, you end up with, let me see if it's on the next page. No, it's not. You end up with an anti-approach, and from the other side, you end up with a syn approach. But either direction, it's allowed. So we're going back to the principle of microscopic reversibility now. The nucleophilic elimination, the nucleophile elimination will break that bond that was formed and reconstitute the double bonded, the carbonyl group. And so it's allowed simply because the addition, the nucleophile addition, was allowed. Now, when we have this bimolecular problem with the elimination reaction, where the nucleophile approaches the hydrogen that's adjacent to the leaving group, remember those conditions. So that bromine is on the beta carbon, hydrogen's on the alpha carbon, and the nucleophile approaches that hydrogen because it is deficient. The carbon there is deficient, and allows the hydroxyl to take that hydrogen and then break the bond between hydrogen and carbon. And when it does that, it produces, let's see, 1, 2, 3, 4, 5. That would give you 5 bonds, right, with the beta carbon. Can't have that. So the bromine has to leave. And that's a good thing because it's a good leaving group. So notice that we're obeying the 3-arrow rule, right? That's just a minor detail. But it's useful in these cases, particularly this bimolecular elimination, to view this in 2 steps. Since we're going to talk about it in terms of overlap of molecular orbitals, look at it in 2 steps. In other words, the first step is where the hydroxyl approaches the hydrogen. Do we get HOMO-LUMO overlap there? Then we would break the bond and release the bromine. So let's look at it in terms of 2-step process. We know it's not a 2-step process. I mean, it's definitely concerted. It has to be concerted because you can't form 5 bonds with a carbon. But it's useful to approach it as a 2-step problem. So that first approach, the HOMO on the hydroxyl, overlaps with the sigma star on that hydrogen. And here again, we have to take his word for it. I can't prove that that's a sigma star and not a sigma. So that's the first step. Now, when that approach happens, we have um, two options. The overlap, in order to form the double bond, the electrons that are being released from that carbon-hydrogen bond will go into the double bond. And the way they do that is for the released orbital for the carbon, alpha carbon, overlaps with the unoccupied, the LUMO from the beta carbon, and you get the double bond. Okay, it's got two electrons that are being released by the hydrogen being grabbed by that hydroxyl. Okay, so the most overlap that you can get, and we have to imagine this overlap as happening in real time, right? That diagram shows on the left, it shows we don't see any overlap there, but the hydrogen hasn't left completely yet. Right? So when it does, then we can get substantial overlap, and that's where the pi bond forms between the two carbons. Okay, this is known as the anti-conformation, because the approach of the nucleophile is opposite to the position of the bromine, the leaving group on the beta carbon. So that's the anti-conformation. But we could also get some overlap if once that remember, you can spin the bond around a sigma, but we don't have the pi bond yet. So you can spin that bond around and put the bromine on the syn side, on the same side as the approach. That's entirely possible. But notice that the way the overlap occurs, you don't get as much overlap with the syn conformation as you do with the anti. So while the right-hand model is allowed, it's not kinetically favored as opposed to the anti-conformation. That make any sense? It's kind of it's like I was dancing around the barn several times and beating the bushes while I was going. Okay, so we're gonna now we're gonna move to electrophilic addition. That previous one was E2. Electrophilic addition versus elimination. So if we can show that the addition is allowed, then the elimination will also be allowed. They're opposite processes. So our let's see. In this approach, rather than, well, we still have the electron rich wanting to transfer electrons to the electron poor. And since the hydrogen and chlorine are together and the bond is very polar, the hydrogen is going to be deficient. Then we can approach it with this these pi electrons, which are more loosely bound than the sigma bonds. So that makes that double bond in there makes it electron rich, and its HOMO is going to approach the LUMO on the hydrogen and produce, well, when it does, and the leaving group goes, we're going to produce a carbocation. Okay, so it should look something like this. The HOMO of the alkene is a pi molecular orbital, so it's electron rich. The LUMO is a sigma star for the hydrogen. Now that makes sense, because when hydrogen bonds, it's only got one electron itself to donate to a bond. And the lowest excuse me, the lowest energy is going to be a sigma bond. So the only thing left, the next highest one has to be a sigma star. That would make complete sense to me. So I don't have to take Dr. Carty's word for this one. But you still get the overlap of that sigma star LUMO with the pi molecular orbital from the HOMO of the, excuse me, of the alkene. So that means that according to microscopic reversibility, the because the addition reaction is allowed, then the elimination reaction should also be allowed. And I think this is the last one in our examples, the carbocation rearrangement. This is a 1,2 hydride shift. It would work probably just as well for a methyl shift or an alkyl shift. So we've got this carbocation, and we want to stabilize it. We know that the positive charge is more stable on the tertiary carbon than it is on the secondary carbon. So we get that hydrogen shift over to the secondary carbon, and now the carbocation lies on the tertiary carbon. Now, we've studied that already. But what does that look like in terms of HOMO and LUMO? Because this is internal to the molecule. Well, the sigma orbital on the hydrogen is the electron-rich species. And the LUMO is an empty p orbital, right? Because that carbon is sp2 hybridized, you've still got a free p orbital that's empty of electrons. And we do get substantial overlap. That's why this only happens between adjacent carbons. And this is also an explanation for that. You can't get the rearrangement on carbons that are 3 positions from each other. They have to be next door neighbors in order for this shift to happen. I think that's it. Yep. That's it for Inner Chapter C.